Alright, we're going to look at a technique in Cal 1 that's developed, and that's called U substitution for integrals, and it's kind of like the backwards of the chain rule. So for example, if I take the derivative of 2x plus 5 to the third power, if we apply the chain rule, we're going to use the power rule first, which is the 3 comes down, and then it's the base, 2x plus 5, and subtract 1 from the exponent, which will make that to the second power, and then times the derivative of the inside, which is the 2x plus 5, and that'll give me the 2. So that whole derivative is going to give me 6 times the quantity 2x plus 5 squared. And so if I know that I have a derivative here, then I can go backwards and find the antiderivative of this. But it's not something real obvious. I mean, one thing we could do is we could FOIL that all out, but if I give you something to the 100th power, then that's not going to be very good and very impractical to expand out. So here's our antiderivative, and so what I'm going to look for is I'm going to look for the inside function, or what's something in the denominator is kind of the general technique, and the more practice you get with these things, the easier they get. So kind of the inside of my function here is the 2x plus 5, and so that's what we'll let the letter u equal. And when we take the derivative, du is equal to 2 dx. And the goal here is to replace all the x's with the letter u, and then we'll have a simpler integral to take care of. So I got the 2x plus 5 is replaced with u, and then I have the dx is almost quite replaced. I'd kind of like to get rid of the 6 there also. I got a 2 here, so what I'm going to do is I'm going to multiply this equation by 3, and that should do it for me. So we'll have 3 du is equal to 6 dx, and so the 6 dx is replaced by 3 du, and the 2x plus 5 is replaced by the letter u. And so what we have is something quite nice to find the antiderivative of. So it just becomes u squared times 3 du, after we do that substitution. Then we'll take the antiderivative. So I know how to take the antiderivative of u squared. It is to add 1 to the exponent, divide by that exponent. We had the pre-existing times 3 there, and then plus your constant of integration. So the 3's will cancel, and you have 2x plus 5 to the third power plus your constant of integration. So we do get back to the original function plus constant of integration, because we don't know what our initial conditions are. So it is the antiderivative of this. Okay, we're going to do a few more examples of this u substitution. So let's say we have secant squared x divided by tan squared x, and we're looking to take the antiderivative of this. So I'm going to look at the functions. I look at, and I see I have a secant squared, and I have a tan, the tangent squared. And kind of the general rule of thumb for u substitution is a lot of times you want it to equal the denominator, not the full denominator, but the inside part of the denominator. And the inside part of the denominator would be tan x. And I'm going to look at what the tan x is, and the derivative of tan x is secant squared. So that's looking good to me. So we're going to let the u equal tan x. Then du is going to be equal to secant squared x dx. And again, the goal is to replace all the x's with the letter u, so that we'll have a simpler antiderivative. Another route you might have been able to take is to replace all replace the secant and the tan, right? Rewrite it in terms of sines and cosines, and see if that would be something that would be fruitful. Sometimes it is, sometimes it's not, but we're doing u substitution, so we're gonna go with this route. Okay. So the tan is replaced with u, and then everything in the numerator, the secant squared dx, is replaced with a u. So this is looking good to me. So this becomes du over u squared, and hey, that's looking real great. So what we'll do is, it's really u to the minus 2. So when I take the antiderivative, I'm going to add 1 to the exponent and divide by that exponent plus the constant of integration. And then we'll just go ahead and replace. U was originally tan x. And if you want to write the reciprocal of tan is cotan. If you want to write it as negative cotan plus c, that's fine. Or if you want to leave it as negative 1 over tan x plus c, that's fine too. I'd probably want to do the negative cotan though. Okay? And then if you take the derivative of this, you should get back to this secant squared over tan squared. Okay? Well, let's try another one. Let's say we have x to the 5th divided by the cube root of 1 plus x to the 6th. Again, this is something that's not obvious. It's not like the sine or the cosine that we know. Things like secant squared, the general power rule, something we don't know. So the only other technique we have at this time is U substitution. And kind of the inside function here, the most innermost function is 1 over x, or it's the 1 plus x to the 6th. And that's what I think I want to let my U equal. And you can try different things. Well, what if we let U equal the x to the 5th? Does that help me out? Maybe not. So it might be a little bit of trial error in terms of what the U and U should be. So du will be equal to 6x to the 5th dx, which is like really close to what we have there. Upstairs I have an x to the 5th dx, so I'm off by a factor of 6. Well, we can divide both sides by 6 and have du over 6 equals x to the 5th dx. So the x to the 5th dx will replace everything upstairs, and the u will replace the 1 plus x to the 6. So this becomes the antiderivative of du over 6 times 1 over cube root of u. Okay, so that 6 in the denominator is just hanging out as a 1/6. And then we have u to the minus 1/3. So I'm going to add 1 to the exponent, which makes it 2/3, and then divide by that new exponent, and then plus our constant of integration. So it'll be 1/6 times, when I divide by a fraction, I take the reciprocal. The u is 1 plus x to the 6th to the 2/3 plus constant of integration. And we'll simplify that to be at 1/4 plus 1 to the x to the 6th to the 2/3 plus your constant of integration. And then if you want to take the derivative of this, you should get back to the original integrand, just like what we've done before. Okay, I think I got 1 or 2 more examples. Yeah, maybe it's just 1 more. Alright, let's say I want to find the antiderivative of x times the square root of 2x minus 1. And I look at it, and it's nothing real obvious to do here. It's not a power rule. It's not some trick function that I know, so I'm going to poke around and try U substitution. So the inside function is the 2x minus 1, so that's what I'll let the U equal. Then the du will be equal to 2 dx. And I have a bit of a problem here. So the square root is now going to be the square root of u, which is good, but I still have that x out in front, and I haven't replaced that. So I have a bit of a problem if I want to do u substitution. Okay, and du over 2 is going to replace the dx. So I've replaced everything except for that x out in front. And so kind of to push this u substitution a little bit further is I'm going to take that original equation of u equals 2x, and I'm going to solve it for the x. So I'm going to add 1 and divide by 2. So add 1 and divide by 2, and that's what my x is going to be. And now I have everything in terms of the letter u. So we go ahead and plug all that stuff in. Okay. And I'm going to go ahead and factor out a 1/4 because I got a denominator of 2 here and a denominator of 2 here. That's going to be a 1/4, so we're going to pull that out. And then we have u to the 1/2 times u, which will be u to the 3/2, plus a u to the 1/2 du. And now that's something that I know how to take the derivative of. I'm going to use the general power rule, which says to add 1 to the exponent and divide by that new exponent. Okay, so we got a 1/4. And u to the 5 halves, and when I divide by 5 halves, I just take the reciprocal and multiply, which would be 2/5. Then I'll have u to the 3 halves times 2/3, the reciprocal, plus constant of integration. And then we'll go ahead and replace the u's with the 2x minus 1 to the 5 halves, plus 2/3, 2x minus 1 to the 3 halves, plus your constant of integration. Okay. Now if you take the derivative of this, you should get back to the original integrand. If you're using some sort of technology or like Wolfram Alpha to check to see if you're doing it correctly, Wolfram Alpha is going to take it a little bit further. And one of the techniques we've used in the past, which I'm not going to do here in the interest of time, is they're going to factor out the smallest exponent. So we'd factor out a 2x minus 1 to the 3 halves, and things will kind of end up being packaged a little bit nicer than what we have here. So if you were checking it with some sort of technology, this isn't the correct antiderivative. It's just technology may package it a little bit more fancy.